Hello everyone. Let's get started. We'll be discussing a few things about TFLearn, which is a wrapper. So let's look at the agenda, what we're going to discuss. First of all, we want to see what TFLearn is. Then we'll be discussing building model in TFLearn. What are the steps? What are the sections of it? And I have similar 3 use cases, MLP, CNN, and RNN. Using this on TFLearn, we have a lot of examples for autoencoders and GANs and other architectures as well. So that's an agenda from the TFLearn side. And as I said, I have included a section from my side. And the section is going to be on different optimization algorithms we have used. And sometimes, if you recall, whenever you were discussing the LSTM, I said RMS prop help you in tackling the problem of gradient exploding and vanishing. TFLearn is again a high-level API for TensorFlow. And when we say high-level API, basically what we mean is that most of the functions in TensorFlow have been kind of summarized. So there are a lot of number of lines of things which we need to specify as a data scientist when you are coding through TensorFlow. But what these higher level APIs do really is they make a lot of things default and use it for predicting. And you can write the number of line of code which are there in TensorFlow with a very small, like 1 or 2 line of code. And I'll show you how we can do. And we have already seen in terms of Keras that through 1 line of code, you can fit the model easily. And just 2 line of code, you have specified everything. And most of the things have been defaulted. There was the benefit. And if you want to improve and if you want to change, you can do it the way you did it in TensorFlow. But here it will be very simple exercise. And these benefits are available in Keras too. That first, it's easy to use and understand. So it's the same thing which I said, that is less number of lines and simpler syntax to write. Fast prototyping, and that's what we have discussed. It has a lot of benefits like layers, regularization, optimization can be written in 1 line of code. Full transparency over TensorFlow, basically you can see what function you are running and what really happening. There are a lot of helper functions available here, which I'll show you in terms like multiplying inputs and output and optimizer. And most of those functions which were there in TensorFlow in terms of like Adam optimizer, RMS prop, these are also available here in a similar or even simpler way. Graph visualizations, you can still use TensorBoard even top of TFLearn. So the way I showed you kind of graph through TensorFlow, you can also connect TensorBoard with TFLearn as well. And they are very simple 1 or 2 line of code. And in fact, you can do it within the code itself. And it works with both CPU and GPU. And some of you would be wondering that not much of a difference from what we have already seen from the Keras one. It was the same, all things were there when we discussed Keras. And these are some of the features coming back to the slide. The layers, built-in customizable functions, and training, evaluate, and predicting. These things were also available in Keras, and here it also provides a similar or even simpler implementations than TensorFlow. Layers would be the same layers which we have been discussing, the dense layers, the convolution layers, and the RNN layers. Built-in functions, all those Adam, and there are a lot of functions we have been using. You can customize these functions. So as I said, there are a lot of default values which we are not supposed to change. But it has an flexibility that if you want to really change, you can go to the code and make the similar changes like we did in TensorFlow. Training, evaluating, predicting. So training and evaluating is the same, like you can train and evaluate how good your model is doing. And the predict function work for predicting for newer examples in your dataset. So that I have already discussed what these layers are. This is an example to showcase that how really your TFLearn is minimizing or creating this. On top you have 5-6 line of code. So in the first line, what you're doing is you are randomly initializing weight of that size. So let's say we are trying to do a convolution neural network. So first we are defining the weight of 5 by 5 matrix by 1, probably it's a black and white image. Then number of filters 32. That would be float type, and we're giving it a name. Then we're creating the bias, and we are creating 32 bias values of random values, random normal, and it will be float type and name. Then we are creating a convolution 2D. You are specifying the input, you are specifying the weight, then you are specifying the stride. In stride, if you recall what was the stride, the number of spike pixels your filter is skipping at next time. And padding is same, and if you guys recall still, the padding was, this is your image, and what padding used to do is it create 1 layer of zeros around the image. so that your filter can still go beyond and get the information from your edge values. So you need to define all these things, then you add bias by this function, then you apply ReLU. This is the syntax of writing one convolution layer in TensorFlow. But like we have seen in Keras, we can very simply can do that. We are writing a convolution 2D from TFLearn. So first we need to install and import. These two things I think common across all the Python libraries, that first you install platform and then you import it to a particular program. Then you're trying to set up a layer called convolution 2D. X is the input, 32 is number of filters, 5 is basically 5 by 5 metric you're fitting in, and then activation function you're fitting in ReLU and you're giving it a name. So it is very similar the way we have seen it in Keras. The only difference is that there we were putting the input values later in the code. Regularization, all these are built-in functions. Before I go in details, let me take a step back and help some of you understand that what these regularizations are. If you recall, one of the regularizations we have discussed, and that was dropouts. So regularizations are actually being used for removing this overfitting problem. And overfitting, if you recall, is that your model is doing pretty good prediction on the training data set. However, it is not going as good prediction on the test data set. And we call it that the model is not generalizing well. And what we do is we need to make sure that your model also generalizes well on the new data set. And how do we really do it? I was saying that one of the ways you can do it is you can bring in the dropout. And what dropout does, let's say this is the architecture of your model. This is your input layer and these are two hidden layers. And let's say this is your output layer. What we'll basically be doing is that all these connections, let's say it's a densely connected layer, all the connections it may have, everything is connected to everything else. So what we were doing is that we randomly switching the nodes in hidden layers off. And what the impact was that if you switch off some of the nodes randomly in every epoch, and these switching off would be changing between and among the nodes, what really happens is that model will not be able to memorize that how much should be the weight here, how much the contribution of this, and how much the contribution of this. So your model will not be able to memorize the training set, and once it's been trained, you can use this model for predicting the test data, and it will be generalizing better. That have been seen. Another way of regularization technique is called L1 and L2 regularization. And basically from implementation sides, they are very, very similar. And name comes from the fact that what kind of regularizations you're using. So let me give you an intuition, and implementation is there in the code, so you would be able to understand what's really happening. Let's say you have some X and Y values. You have some input and output values, and you're doing some prediction, Y hat, and the predictions are there. And let's say it's a classification problem. So you guys know how we used to do the loss between the actual and predicted. There was, let's say, cross entropy we are using. And cross entropy basically is the magnitude of difference between actual and predicted. And if you recall, the function used to be yi log of y hat, something like this, okay? And what it actually does is that if this is 1 and there's a minus in the beginning so that it can be minimized. So what really happens is, if the y is 1 and the probability of this being 1 is, let's say, 0.99, it means very, very close. If it's close to 1, then it will be very, very small number, like 0.000 something. But if this is 1 and the probability is 0.2, then you can see that log of 0.2 and then negative would be a higher value, let's say 0.9. So what basically we do from this process, from the loss, is that we are trying to see that how much is the difference between the actual value and the predicted value. And we have seen it that how the way cross entropy work. I'm not going in details. The point of discussion is this L1 and L. So let's discuss the L2 first. So the loss function used to be 1 over m, and if I just write this something like this, y and y hat. So let's say I, and let me write a summation of it. That used to be our loss function, and what were objective that we should be able to reduce the difference between actual and predicted. And we have to, every time, if you recall, whichever optimization function we used, we always try to minimize it, either gradient descent, RMS prop, or ADAM. And as I said, that these are just a variant of gradient descent algorithm. we were trying to minimize this function, and we have seen that way we can minimize it, that the value of yi is equal to the predicted value. But in the process of learning, when we run our model for multiple iterations and the way we have designed this model, our model would be trying its level best that it should be able to reduce the difference between these two values, actual and predicted. And in the process, what really happens is that your model would be trying to fit, let's say these are two classes you have. So what your model actually tries to do is it tries to fit a line which is such non-linear that it kind of memorizes everything what's there in the training data set. Let's say this is the line your model has fit, and it is doing 100% prediction for your training data set because it's a very convoluted line. But basically what you're looking for, a line which would be something like this. If there are two classes, even though there's some misclassification happens, you should be fine given that it does the good accuracy on the test set and is something like less non-linear line your model can fit. One thing you will observe whenever the overfitting happens, that the values of the coefficients, and let's say for now I'm writing y hat is equal to wx plus b, only let's say you have these two coefficients. Whenever the overfitting happens, you will find that the coefficient values of these w and b will be going very, very high, and you can see it whenever say overfitting happening. You will see that values of your weights are gone high because now you need to find a lot of drastic changes in the line at multiple places. Now coming to mathematics a bit. Let's say any function, you have 3x plus 2 and you have a constraint that x cannot be or less than 0. Suppose this is the constraint you have put in. This is the equation 3x plus 2. I want you to find that what is the minimum value of this function. Then you will try, it cannot be less than 0, but at what value this would be minimum value from this function? When I put x equal to 0. So if you put x equal to 0, the function value is 2. Let's say you have 3x, and against the same constraint which I said that x cannot be less than 0, whatever constraint it's been written. So what is the minimum value you can put? That something very, very close to 0, or in fact you can put 0 because that's not constraint. And the minimum value from this equation can be 0. Now let's say I have added some constant, let's say something like this, and the same constraint remain. Then to make this value minimum, I have constraint on this that x cannot be less than 0. This is this. If I need to minimize the value, or I need to get the minimum of this equation, I have to bring the value of w as well as minimum as possible. This process is being used in kind of forcing your model to learn less complex weights. And let me go back to what I was discussing earlier, that your loss function used to be something like this: 1 minus m summation of your loss function between y and y hat. And what really been done to make sure that my weights in the equation are being kind of suppressed, what I do is I do this addition which is called lambda over m, and whether you add m and not does a lot of stuff. But let's say you have added second order norm of all your weights. So what really happens is when you're trying to minimize this equation, you have added this extra term into your loss function. And all the weights which you are using, like w1, w2, as many weights you have, basically this w square, what I have written, is actually means w1 square plus w2 square up to all the weights I have. And now if you look at the equation of my loss for the particular model, what I'm trying to do is I'm trying to minimize this entire equation. And if I have to minimize it, then I have to minimize this particular term. And if I really force this model to kind of fit a straight line, I can increase the value of lambda. And if this value is very, very high, to minimize this equation, I have to make all my w's closer to 0. If your w's have become very, very close to 0, let's say that was your equation which you are using, so forth. If you really need to fit a line which have all the values very, very close to 0, like this is close to 0, this is close to 0, means you have very limited amount, and your line may not have a very convoluted image, but it will be more or less like a straight line. And you can try that whenever the weights are kind of close to 0, what kind of equation it really fits. Coming back to what I was trying to say earlier, that adding this particular equation, adding this particular term, you can force your model to minimize w's, because now you need to, in the optimization process, your objective is to minimizing the loss. This lambda again is a parameter or hyperparameter which you need to train. In most of the algorithms, we manually don't change it. I think 99.99% I can tell you that you will be using the default values, but you can play around with these values, that how much force you need to apply in terms of minimizing or in terms of regularization. And you can easily see, as I was saying, if I keep this value high, very, very high, let's say I put it 100 or 1000 or any high value, then I'm forcing this equation that it can only be minimum only when my W's have almost become zero. Because this term is kind of not relevant, that whatever equation happens here, this value which is very, very high, all I'll be trying it, that this W's are kind of brought it to zero. This kind of normalization or regularization, because I'm forcing my weights to be get lesser and lesser and getting my hypothesis or separation more simpler than the earlier more convoluted line. I'm forcing it more simpler line, and this particular way kind of reduces the overfitting problem. This was L2 type, and in fact L1 is exactly the same. The only difference is here we were discussing loss by adding lambda and the second order magnitude of your weights. When you say L1 normalization, what you really mean is that you are adding a regularization term, and the lambda is called regularization parameter. You are adding first order norm of your weight, and what it really means is the W, it is nothing but summation of your absolute weight of W1 plus absolute weight of W2, and so on and so forth. L1 and L2 norm are being used for removing the overfitting. Most of the time you will see that people are using L2 regularization, given that it reduces your weights for W's exponentially and very, very slowly in comparison to L1 norm, because these are absolute term. I'm not going in mathematics, but you can see the gradient of these terms. It's kind of helping in making most of the weights or some of the weights to zero directly. So L1 norm is also being used sometime in identifying what are the most important features if you're doing logistic regression or regression kind of problems. And L1 and L2 norms are in fact being used in logistic regression earlier to remove the overfitting. It's not a new technique, it's a very old technique, but now because we know how we write the loss function for our neural network, we can also introduce these two terms, L1 norm or L2 regularization, into your neural network as well. But dropout is more conveniently being used, and L2 norm is being used more than the L1 norm. There are some custom functions which all of us gone through, like prelu, I don't know, or elu, I'm not sure. But most of the functions like linear 10H, sigmoid softmax, soft sine, relu, and leaky relu, objectives like cross entropy, binary, as well as categorical, mean square, hinge loss. Basically, these are some calculations for calculating the loss. SGD stands for stochastic gradient descent, and it is even a further minute version of batch gradient descent. And rest of the things like ADA-grad, FLTR, ADA-delta. When I discuss the RMS prop and ADAM and momentum, you will get an idea that different variants, when I say that this is a variant of gradient descent, you would understand that we will be making some minor changes in how the calculation is happening in the back end. The real core of gradient descent doesn't change, that it has to compute the gradient and then identify how much and which direction the weight needs to be learned, and we will be controlling it by different parameters like learning rate and epochs. But we also have some other ways and tricks and techniques that you can make the process of this gradient descent faster and sometimes more robust. So all these variants like RMS prop, ADAM, and momentum, all these terms are just helping the gradient descent process do faster. It's not that this is something new altogether. All these three things, RMS prop, ADAM, and momentum, are basically the same gradient descent learning algorithm with the minor changes. Metrics like accuracy and top K. Top K is like what is the top K classes which has been predicted by the model. Let's say you have 10 classes. What are the top 3 classes your model is giving highest probability to? Initializers, so 0 is like you're initializing a weight to be 0. Uniform distribution, uniform scaling normal, truncated normal, Xavier, variance, scaling. L1 and L2, I'm sure you would know it by intuition that what these are techniques to kind of make your model regularize better. And L2 is kind of, it reduces the weight slowly. And L1 norm, because it takes the absolute value of your weights, then it kind of reduces the weight sharply. That's the only difference. But the analogy we have seen that we add a term to our existing loss function so that you can control the weights in a way that it doesn't overfit or doesn't fit a more complex or convoluted line to separate. So these were some of the things which are available. Predicting is more or less same, just like in Keras that you can fit convolution neural networks TFLearn.conv2D. The only difference is this regression. So this regression is actually doesn't mean a linear regression. You can think of this regression actually the way we used to do compile in Keras. If you recall, what we used to do in Keras, that we write these all layers, that first you write convolution layer, then you write max pooling, then convolution, then max pooling, then flattening, and then the last output layer with some hidden. And in the end, if you recall, we used to do something like this, model.compile. And in model.compile, what we used to do is that we will be giving the last layer of the model what we have fit in, and then we'll give what the optimizer we are using. Either we are using gradient descent or Stochastic RMS prop or SGD, and then what was the loss function. This is same only thing, don't get confused with this regression line, it's more of like compile. And then rest of the things are same. The DNN stand for deep learning network, and then you're fitting the same way we used to do it in Keras as well. And using the model, so once the model has been trained, you can load the model and you can predict the model with the predict function. And I have a few codes, and as I said, I have ANN, CNN, RNN implementation for all of them implemented for you, and I can show you what is the syntactical difference between Keras and TFLearn. So there are functions you can provide in the model itself, and I'll show you how you can do it. And you can give the values 0, 1, 2, or 3, and what do they really mean? That if you give TensorBoard value 0, then it'll be giving just the loss and metric values, the weights. If you give 1, it will be giving the 3 value outputs. If you're giving 2, when you run 3, it will be giving you all these things for the model. It'll be kind of model structure, weights, loss, and all these metrics which we require for model prediction, as well as doing the debugging. So it's very simple. When you're training the model, you can fit, let's say, deep learning network. The network is the name of the model you have fit, and there would be a few lines which would be in the network. The CNN model in Keras, we started the model as classifier equal to sequential, and then we keep on adding the layers to the classifier itself. And key classifier, we first add convolution. So this is the same thing that we are adding, and the final layer, you can say that you set up a deep learning network for this network which we have initialized on the top, and we are giving TensorBoard verbose equal to 3. In the last page we were seeing that what does this 3 mean. So if we specify 3, we mean that in the TensorBoard we want these outputs. But if you see that it says best speed and best visualization, so if you run these things, your model would be taking some time to kind of store the values. And by default, that's the reason I was showing you in the beginning of the class, that when you run the TensorBoard, it will be saving the file it will be creating a folder in your directory where you're calling the code from, something like this. And this name is something which you gave in the model while opening the TensorBoard. In a similar fashion, it will be creating a file which you need to visualize in TensorBoard. But by default, it creates a file in a temp folder. If you want to be there in a specific location, you can give the location by a function. Here itself, you can specify the path and where you want to save the folder. It's basically a directory path. This is how you can save these weights. So model.save will save in this particular format, and if you want to load it, you can load it again. And once you load it, and this is the same process I was talking about, that end of the day, you have a static model with all the learned weights, and you will make it pass through your new data set, and it will be making the predictions. So what you do is, once your model is trained, you can save it in this particular format, and if you want to load, you can load. It will be creating a file, a tf.learn file into the system, and you can load it later purpose. You can see the same process is available in Keras, where you import the model in the form of .h5 and JSON and then use it later. The use case implementations for TFLearn, and over there I'll be discussing a few things about learning process. So now I quickly go through the 3 implementations which I did in TFLearn. Let me zoom it up. The first implementation is that you're trying to predict image classify. This is the data on MNIST dataset, and I think we have seen this dataset when we discussed the autoencoders. So this is around 60,000 images, where 50,000 images are trained in, and 10,000 images into text group. These images are 28 by 28 pixels, and these are black and white images. So it is the reason that we are importing it, and when you say one hot means true, that it is creating different vectors for different 10 classes. So because it's a digit data, you can easily see that we would be having 10 classes, and we have created one hot vectors for all the classes. And what I mean is that for 0 we will be presenting something like this: vector of length 10, 1 2 3 4 5 6 7 8 9. So 10 classes all these examples we have. So for 0 we may be representing something like this, that it has 1 here and rest of them are 0. And for 1, the same architecture, I'm not drawing it again, but it will be 1 here and rest of the place is 0. So this one hot encoded means this, so that it's easier to do cross entropy calculations. Then once the data has been imported, we are creating the deep neural network architecture. So what we are doing is, first of all, we are creating an input layer. And that's the difference between Keras and TFLearn, because if you recall, we were not creating layer for input layer in Keras. We directly used input as one of the parameters in the code itself, but here we need to explicitly specify what the layer is. So we'll be doing it TFLearn dot input data, that's the syntax, and shape is equal to none and 784. And why it is that none, we are specifying that we are not telling how many examples we're going to use, but 784 is the number of pixels in the image, because the image is of 28 by 28, and you can multiply these two, it will coming around 784. And because the channel is 1, because all the images are black and white. Then you create dense layer 1. What we are doing is we are inputting each pixel value in this particular format, not the grid format. So these are all your 784, and then we are creating a fully connected layer. We are taking the input layer which we have initiated on the top. We are creating 64. So what 64 is doing, we are creating 64 nodes in the first hidden layer. So the number of node is 64. Activation is 10h. So we are using 10h activation function. And then regularizer L2. So we are using L2 regularizer, if you recall what it was. And we will be using, when we will be calculating the loss, it will be added for the weights from this particular layer, because we will be using some weight. If you recall what was L2 regularization, that we add lambda plus the L2 norm of all your weights, because we are using weights here. That's why we are using L2 regularization. Weight decay 001. So let me come to it in a moment, but what weight decay means is that we are reducing the learning rate in each epoch, and I'll come to it why it is important. But weight decay is the process of where we can keep on reducing the learning rate in multiple processes in each epoch, what I mean. So this is the process we'll be reducing the weights, and then we can add a dropout layer again on top of it. So here it was regularization through dropout, and very easily we can add tflearn.dropout dense layer 1, and 0.8 means that we are keeping 80% of the node, and 20% of the nodes we are automatically switching it off. And through this process we would be able to reduce the overfitting problem in our model. And we fit the second line automatically, and if you see that this dropout 1 output becomes input for the second layer, we specify activation and regularizer, and again the dropout, and then the final layer is the fully connected layer with 10 nodes. And why 10 nodes? Because we have 10 classes, and activation is softmax. And you guys know softmax creates probability for each class in such a way that it sums up to 1 for all the classes. So what it will be doing basically, that it will be a vector of 10 output. I'm not writing it, but there will be 10 length vector from softmax, and there will be probability for each digit. So let's say for this particular example belong to 0, the probability is, let's say, 0.5. This is 0.001, and rest of them, and final value would be that probably the highest probability is for 0, and rest of them are very, very less. The model is predicting that this particular example belongs or is equal to 0, and then we will be checking it, how does it really work. Regression with using SGD with learning rate decay and top 3 accuracy. So what we are doing is, let me select it. SGD, we have discussed what SGD means, that stochastic gradient descent. It's updating the weight at each iteration. We are starting the learning rate at 0.1 and learning rate decay is 0.96. I'll explain what does it mean. And decay step is 10,000. So these two involve in terms of using minimal, and basically how does it work is that you'll be reducing the learning rate at after each epoch, you'll be reducing it, and this is the step. And when you say that TFLearn matrix top K3, It means what you're doing is, let's say your example is 0 and your model, which is using softmax, end of the day it will be predicting the probability for an example to belong to some class. And as you guys know, what softmax actually does it, as I was showing earlier, that it will be giving probability for each example that which class it may be belonging to. So as I was saying, probably belonging to 0, the probability is 0.5, belonging to 1 is 0.001, for 2, the probability is let's say 2, and for 3, it's let's say 0.2 again. And because now if you see 0.5, 0.2, 0.2 is almost 0.9, and this 0.001, so rest of them would be very, very small. So the model is saying that this particular example belongs to either 0, 2, or 3. This is their top 3 predictions from the softmax, and actually it was 0. So how it's normally been done is to see whether your training example belong to one of the top 3 predictions or not. It is one of the ways of seeing whether your model is really working or not, and how many times your model at least come to a position where it was the actual value was available at least in one of the top 3 predictions. That's one of the ways of seeing that. And then, as I said, regression, TFLearn.regression is the approach which we used to do in Keras, something like model.compile. And when we are doing compiling, we are saying that we are calling a softmax optimizer, we are calling optimizer SGD, metric is top K, and loss is cross entropy. And then your net is being set with all these parameters on the top. And then finally, you are running this. In Keras, it used to be fit, that model.fit. So here we are calling tf.dnn. DNN stands for deep neural network. You are calling the network which you have started, and TensorFlow verbose equal to 0. And if you recall, tf.verbose equal to 0 meant just the weight and I think the loss. We don't require other things. And then once the network is being set, then we fit the model with actual inputs and output. In Keras, it used to be only one line of code for fitting. Here we need to call explicitly this deep neural network architecture so that we can specify we are fitting the net into the architecture. Then we again call the fit function. So after this, once you have specified the network, the process is same as it was in Keras, but that's one additional step which you need to take. And I'm running it for X and Y, which I specified on the top. Number of epochs is number of times you need to run it. Validation set are test X and test Y, and show metric equal to true, and you can give it model name as dense model. It'll run for as many iterations and give you all the statistics like top 3 accuracy, how much it was, and top 3. This is on training for first one, and then how much time it took to run, around 10.9 seconds. But you get to see that how many iterations it ran for, and it's showing 55,000 iterations because we are using a stochastic gradient descent. Each item or each training example is being used for updating the weights. So that's how it's updating its weight so many times. And you can see on the right all that stuff. So it's running for all the example. It has gone through one by one to update the weights in 20 iterations. Bye-bye.